look at some examples of sketching the graph now that we have an idea of the different shapes that we can come across. Let's do this example. So at first glance, we should recognize that we're dealing with sine. There's a negative, right? And the fact that there's a coefficient for theta, I automatically know it's not one of my circles, because the circles needed to have a coefficient of 1. So I know this has to be a petal. And because it's a 5, it's an odd number, I know there has to be 5 petals. If it was even, it'd be double the number of petals. Now, I don't know exactly what my graph is going to be yet, but this is a good start. And I know this tells me that the tip of a petal, the biggest a petal can get, is as far as 3. So this would be 1, 2, 3. So this circle here is as big as one of these petals can get, and I know there's 5 of them. I always like starting at the place where I call the 4 corners, right? These quick and simple ones. That's why we still use a table to guide us, to help us find these points. So by plugging in 0, that's going to be negative. I'll start up here. I'll just do it right next to it. Negative 3 times sine of 5 times 0. Well, 5 times 0 is 0, and sine of 0 is also 0. So negative 3 times 0 is going to give me 0. So if I'm facing in this direction, remember, we always look in the positive direction, but my r is 0. That tells me I have a point right at the origin. But something else, because I didn't get anything in this direction, that tells me there is going to be no petals pointing in either one of these directions, because let's not forget sine is going to have symmetry over the y-axis. So because I got 0 in this direction, there are no petals here. So that means the petals must be either in this portion, or here. So that's super useful. So let's now look in this direction to see if, because I know there's no petals here, maybe somewhere in this direction there might be, or somewhere down here. So let's start with pi over 2. Pi over 2, so negative 3 times sine of 5 pi over 2. Now be careful, because I am facing upward, or in this direction right now, right? Because I'm rotating pi over 2. Now what value I'm going to get, this is going to end up becoming 5 pi over 2. But that doesn't mean that's the position I'm looking at. The position is still at pi over 2. So that'll be 1, 2, 3, 4, 5. So I'm still, we rotated and landed back in the same position. For 5 pi over 2, of course, and sine of 5 pi over 2, that's the point, 0, 1. So I know sine is equal to, sine of 5 pi over 2 is equal to 1. And then negative 3 times 1 gives me negative 3. Now this is where we have to be careful. Yes, I counted 1, 2, 3, 4, 5. But that was because there's a 5 as a coefficient. And 5 times pi over 2 becomes 5 pi over 2. But that's just evaluating at sine. That would give me 1. And negative 3 times 1 is negative 3. My theta that I'm rotating is still just pi over 2. So I'm facing in the upward direction, but my R is -3, so it means I have to go backwards. So my next point is here at 3. And remember what I said, the nice thing about this number, that tells me the largest a pedal can be is 3. So the fact that I'm as far as this circle of 3 tells me I must be at the tip of a pedal. And since we're dealing with sine, I know we must have symmetry. So it has to look something along these lines. And I already know there's no pedals here, there's no pedals here, so I need 4 more. Now, I've already checked in this direction, I need to start checking in between just to see what we get. So let's start with one that we should know, pi over 4. So that's going to be -3 sine of 5 pi over 4. When I plug in pi over 4. So 5 pi over 4 is 1, 2, 3, 4, 5. And since we're dealing with sine, that's going to be in the negative. And at the 4s, we always get square root of 2 over 2, and that's going to be a negative. And -3 times negative square root of 2 over 2 would be +3 square root of 2 over 2. Now this value is approximately, if you plug it into your calculator, if you plug this in, right, let's look here, that should give us approximately, wrong one, I wanted to go here, so we have 3 square root of 2 over 2, that's approximately 2.12. 2.12. If we go back, so let's just say 2.1. So at pi over 4, which is perfectly diagonal, right? If I go perfectly diagonal, I'm going to be at 2.1. So it's somewhere along this line right here. And then let's check a little bit further in this direction, which we know is pi over 3. So -3 sine of 5 pi over 3 is equal to, well, 5 pi over 3 is 3, 6, go back 1. And then we're here, which is the same point as up here. That's 1, 2, 3, 1, 2, 3. So the y value is square root of 3 over 2. And since it's at 5 pi over 3, that's where y is negative. So it's going to be -3 times negative square root of 3 over 2, which will leave us with +3 square root of 3 all over 2. And this is approximately equal to 2.6. So now that we go further out, it goes to 2.6. Right, something along these lines. So to me, it went from 2.1 to 2.6. That seems to me that it's getting closer and closer to 3. So if I go in this direction, that I might have a pedal here. And if I go based off of symmetry, that must mean I have another pedal on this end. And remember, I need a total of 5 pedals. So I must have a pedal here, and then I must have a pedal here. Because I need 1, 2, 3, 4, 5 pedals. If I have points on this side, remember, this has symmetry on the y, so I must have those same points on left side. But then I have 3 pedals, and I know for sure I didn't have any horizontally. So I must have 2 in this direction. Of course, it should be going out to as far as 3 because that's the tip. But let's look at exactly what this graph looks like. Again, doing by hand is always going to be a rough sketch, but the goal is to get as close as we possibly can. And if you notice, we weren't perfect. Again, I probably could have picked some radians in this direction, but we did pretty good with these two. That's all I'm looking for. Now, is that going to always be the case where you need that many points to help you graph? It's not going to always be the case. Some situations, we can just do it with a couple points, and that's going to be how our next one is going to work a little bit. We won't need as many points because looking at this next equation, well, when there's a constant term and this trig function, I know I'm dealing with one of those circular, it's not a perfect circle, but does have circular shape to it, which is this graph that I'm pointing to, which we'll look at after. But right now, I know it's one of these 3. Now, like I said, I did give a bunch of descriptors on what to look at. But first, since it's a sine and this is positive, I know whatever I'm doing is going out in this direction, right? If these were the same, then I know that's a cardioid. But the fact that they're different, I know that it's either going to be a dimple or a loop, right? The one that looks like an apple versus a loop. But sometimes it's hard to remember which one is which. So, but something that you can remember is sine, and since it's positive, it's pointing in the positive sine direction where all the positive y values are. Hence, I can go back to my table and I can point in this direction. So in that direction, I have pi over 2. Now plugging in pi over 2, I'm here at the bottom that don't have room, or I probably could here. Right, I can write 4 plus 6 times sine of pi over 2, which pi over 2 is 1, right? This is equal to positive 1. And then 4 plus 1 is 4 plus 6 is going to give us 10. So, for the sake of this example, we're going to say this is 2, 4, 6, 8, and then 10 up here. So I know I have a point at this very tip. Now, it's either going to be a dimple or a loop. Now, that's going to happen based off of, now I'm going to look in this direction. I'm going to try to see what happens if I face this direction, which I can do it 2 different ways. I can do 3 pi over 2, or I can go in the opposite direction to make it quicker, and that would be negative pi over 2. And that's going to give us 4 plus 6 times sine of negative pi over 2, which would be 4 plus 6 times negative 1, which that's going to give me 4 minus 6 is going to give me negative 2. So in one I had 10, and the next one I have negative 2. So this means I'm facing 0 to start, and then I rotate clockwise pi over 2 because it's negative. So I'm going to go clockwise and at this negative pi over 2, I'm facing in the positive direction. But my R value is negative 2, meaning I have to go back in the opposite direction to get to here. But remember what I said. If these 2 points are on the same side of that axis, I know this has to be our loop example. Go here. Oh, it looks funny. Let's go a little wider. And then that should be the exact same graph we have on our Desmos. And that's going to be here, right? And we have everything we need. Now, the only thing you can notice, you can start seeing how we get, for instance, 4 right here, right? Having to do with our constant. If you want more detail, but again, I'm definitely looking for these 2 values, and all I needed was these 2 points. Now, last but not least, let's do one more quick example. Here, it's cosine, so there's symmetry over the x. 2, there's no constant in terms of, this 2 means there has to be 4 petals. So let's start pointing in the 0 direction to make things quick. Let's start at 0, right? I like starting the 4 corners. And then I move this up to give myself some room. That's going to give me 4 times cosine of 0. And cosine of 0 is going to be 4 times 1. It's going to give me 4. So that tells me I'm facing in the positive direction. My R is 4. I need to go as far as 4. That's how big the graph I made gets. But remember, what this constant, this coefficient always does to your trig function, it scales it. So you know how large or how small it's going to be. Because it's 4, I know exactly that the largest petal, the tip of the petal, can only be 4. And that's what we got on this graph. So that tells me there has to be a petal here at 4. And since we have symmetry on the x-axis, we should have a petal in this direction as well. And remember, because it's even, I know there should be 4 petals. Now there can't be a petal here because that might end up giving us our 4 petals that we need, but they don't exist. So then I know the only other way that this can be the next petal is directly in the middle. And we can see that here in this example. Last and final example for these. And it's a petal. And we can see the petal goes as far as 4. And then we have symmetry. And look, I really only needed 1 point. But if you're unsure that I don't know if what I drew is correct, right? Maybe you're debating that this point is wrong. Well, this is why I said just resort back to your table. Test pi over 2. And if I do 4 times cosine of pi over 2, well, that's going to give me 0. Oh, wait, what are we plugging in? Oh, I forgot my 2. Right, 2 times pi over 2. That's going to give me cosine of pi, which is going to be 4 times -1. Right, because we have cosine of pi, it's going to be -1. But -4 times -1 is just -4. And that just means when we point in the pi over 2 direction, we go back 1, 2, 3, 4. And remember we said we have symmetry. So this petal has to match the next one. And then these two petals need to match as well. So again, practice on comparing them, practice on sketching them. And one last thing I want to talk about is how we can go back and forth from polar to rectangular using some of the equations we've worked with. So to go from polar to rectangular, all we need to remember is that sine theta is equal to, once again, opposite over hypotenuse. Now again, we always had 1 in the denominator, or the hypotenuse, because we were talking about the unit circle with radius 1. But now, we're not sure if we're dealing with a radius of 1. But the idea is finding an equation that has a relationship between these two coordinates to be able to get into rectangular form. And these two can do that perfectly with, of course, a little bit of algebra, right? A little manipulation. You can get y to equal r. Get it to equal r sine theta, which is exactly what my polar equation has. And now let me find my y value. And then for the x, it's just going to be r cosine theta. And here's a quick example. Again, these aren't too difficult. To find my y value, I am going to just plug in r, which our r is 6. And then I'm going to plug in sine of pi over 6. And that we know sine of pi over 6. Right, if we do it really quickly, 1, 2, 3, 1, 2, 3, y value is 1. So sine of pi over 6 is equal to 6 times a half. It's going to give me 3. For my x, it's going to be 6 cosine of pi over 6. And cosine of pi over 6 is going to be square root of 3 over 2. The 2 and the 6 will simplify and leave us with 3 square root of 3. So my final answer is x is 3 square root of 3 and y is 3. Now for going from rectangular to polar, it can be a little more challenging, but the concept's the same. I want to be able to find a relationship between x and y and my r and theta. And the perfect way to do that is with tangent theta equaling to y over x. Now, again, the idea is I need to find theta, but the only way to isolate this theta is by using, the only way to get theta is going to be by using the inverse. So tangent inverse of y over x. And then we have another equation. We can use x squared plus y squared equals, sorry about that, equals r squared. And then I can rewrite that into r is equal to plus or minus the square root. Sorry, I'm squeezing this in here. I'm squeezing this equation to get, x squared and y squared. example. So to find my theta, I'm just going to plug in. So tangent theta is going to be tangent inverse of negative 2 over 2, which gives me tangent inverse of negative 1. And you have to remember the restriction for tangent inverse is between negative pi over 2 and pi over 2. And tangent is negative only in quadrant 4. So to get to that 1, negative 1, and that's where both the y and the x are the same, that happens here at the 4's, which it would have to be negative pi over 4. And then for r, we plug into this formula. It's going to be 2 squared plus negative 2 squared. That's going to be equal to the square root. 2 squared is 4, negative 2 squared is 4. That's going to be 8, which simplifies to 2 square root of 2. Now if you notice, I didn't say plus or minus. And that is because when you're using tangent inverse, you can only be, it's only looking at quadrants 1 and 4. But a rectangular coordinate can be in 2 or 3. So that means when you get your theta, luckily this didn't come up in this example because the point that we're talking about, let me make a new little graph. The point we're looking at, if I move this out of the way, the point we're talking about, 1, 2, 1, 2 is down here. Luckily, we can just go negative pi over 4 and go as far as 2 root 2. But when I do negative pi over 4, I'm facing towards quadrant 4. So to get to this point, I need to go forward, meaning that I have to be positive, positive, positive. When would it need to be negative? That's if your ordered pair happens to be in quadrant 3 or 4. Because of tangent inverse, you're always going to get a theta in quadrant 1 or in quadrant 4. And you can try an example of that. I'll squeeze it in here. Negative 1 and square root of 3. I'll give you the answer and you guys try to find it. It's going to be negative 2 and negative pi over 3. So again, it's just because this ordered pair, negative 1, positive 3, square root of 3 is in quadrant 2. Your theta is going to either be in quadrant 1 or 4. But the only way to get into quadrant 3 is you need to choose a negative r. But try converting this point. Here is the answer and test it out.